And then you guys will receive a test before midnight today. Everyone's got a slightly different test, so concepts are all the same, but numbers are different. Test covers first projectile motion, and then properties of logarithms. So you've got some rewriting problems, like we'll see in a PowerPoint today. We've got a couple logarithmic equations, which are new, but you just use the properties of logarithms to solve them. I'll be doing a couple of those today. You've got a couple compound interest formula questions, and you have a couple continuous growth formula questions. Those are like the exponential growth and decay stuff that you guys did for homework today.
Wait, so what does the vectors quiz 2 do?
I'll be looking through that if we need to look at some of the projectile motion questions. I just pulled a couple old quizzes, so you can see kind of what format I'm looking for. Okay, so I'm going to start with vectors. Going all the way back to vector
How do we
addition.
get our tests?
How do you get your tests? I'm going to be sending them individually through WeChat since everybody's got a different one. If that doesn't work, if that doesn't work for you, I can upload all of them to course sites, and you just look for your name. Okay, any other questions about tests or anything before we get started? Okay. All right, so I'm going to start with these vectors. So I've got two vectors here and I want to subtract them. What do I have to do? Okay, I think we lost everyone with Mike. So I've got two vectors here and I want to subtract them. So I'm going to do my x components first. This is 8 minus negative 9 is 17. 12 minus negative 9 is negative 3. I can do the same thing if I give you points instead. So this is the vector from point t to point x. So that vector for our components from negative 6 to 5 went over by 11 to the right. And from 1 to negative 10 went down by 11 units. Okay, minus my vector yz went from negative 2 to negative 6. So that's to the left 4 units, which is negative. And then from negative 1 to 3, which is up 4 units, or positive 4. Okay, if I want to subtract, I can subtract straight across. This is x minus x. Gives me 15. And y minus y gives me negative 15. Any questions on this one?
No.
Okay. Alright, these were a little bit more interesting. So similar to what we've got in the homework, only this time instead of giving you variables, I'm giving you decimals. And we're going to substitute. So if I want to do these, log base 5 of 5 is always an option. And log base 5 of 1 is always an option as well. Okay, if I've got the same base as the logarithm that I'm taking, I'll get 1. If you take a log of any base of 1, you'll get 0. Okay, so here's my 4 options. So what I'm going to do is I'm going to factor this 1 over 49 to get log base 5 of 1 over 7, 7. Okay, that tells me all of these are numbers I can work with. So 1, 1, and 7. Okay, so this is the same thing as log base 5 of 1 minus log base 5 of 7 squared, or log base 5 of 1 minus 2 log 5, 7, which gives me 0 minus 2 times log base 5 of 7 is 1.2, or negative 2.4. Okay, any questions on this one? Okay. Same idea here, only this time I can't directly substitute, so I'm going to factor this 7 over 9 first. So this is log base 9 of 7 over 3 times 3. And I'm going to see if there's any numbers that I can multiply both the top and the bottom by in order to either get 4, 7, 6, or 9. Okay, so I've got a 9 here. I've actually got a 7 as well. So I actually don't need to do anything here. Okay, log base 9. Okay, log base 9 of 7 is 0.9. Log base 9 of 9 is 1. So I've got 0.1. Okay, I'm going to go ahead and change this problem really quick.
Wait, should it be negative?
Sorry, yes. Okay, I'm going to go ahead and change this problem, make it slightly harder. So if this problem had been something like this. Okay, so that's 14 over 12. Okay, when I factor this, this is 7, 2, 6, 2. I don't quite match. Keep going further if I need to. 3, 2. Okay, so what we need to do is we need to multiply by another number on top and bottom in order to match one of these other ones. So I could say something like this. Log base 9 of 7 to 2 over 3 to 2 gives me 7, 4. Oops, missing one. Okay, if I multiply by 2 on top, I'm going to have to do the same on bottom. So I've got 7, 4, 6, 4. If I break this apart, log base 9 of 7 plus log base 9 of 4. And I'll end up with just these two. Maybe not the best example, but my point is we can keep rewriting these logarithms by multiplying by the same thing on top and bottom until you match one of these when we're factoring. You guys did a bunch of these for the homework. Are there any questions on this type of problem?
Mr. Brendan,
Yes.
if we make it like 7 times 2 times 2 and then 3 times 2 times 3 times 2, can we like eliminate the 2's they have at the bottom, and then we can just get log base 9 7 over 6?
You can. So from this step you could have just eliminated 2 here and did 7 and 6.
Okay.
Okay, cool. Alright, a little bit more interesting because we haven't done these yet, but we can use our properties of logarithms to solve equations as well. So with my product property of logarithms, I would multiply these two together. So this would be 3x minus 30 equals 2. or 5 squared equals 3x minus 30. Therefore, 25 plus 30, I'm just going to skip a step, 25 plus 30 equals 3x, and x is 55 over 3. Okay, one more. With my quotient property of logarithms, what's going to happen when I combine these?
They're going to multiply.
If I was adding, then they would multiply. So because I'm subtracting, I should
I mean divide.
divide. Okay. So 2x squared over 8. Then I can rewrite this using my definition of a logarithm. Anytime you don't see a base, by the way, if you don't see a base, you can assume that that log is base 10. If you see an ln, you can assume that's log base e. Okay, so I'm going to rewrite this. This will be 10 cubed is equal to 2x squared over 8, which is the same thing as x squared over 4. Okay, 10 cubed is 1,000 equals x squared over 4. Or I could say 4,000 is equal to x squared. Therefore, x is equal to plus or minus 20 root 10. Any questions on this one?
Do we just keep it radical in the test?
Yeah, you can keep it radical.
Okay.
It's better to keep these as either logarithms or radicals, because then we're not rounding. Okay, jump over to the next one. So what would I have to do here? How can I combine these?
Do you divide?
Divides. This is 2x squared plus 2 over 4. Okay, then I'll do the same things. This is 25 is equal to x squared plus 1 over 2, or 50 is equal to x squared plus 1. Therefore, x squared is equal to 49, or x is equal to plus or minus 7. Okay. So then we've got, I guess I'll do one more. This will be log base 4 of x plus 1 over x minus 3 is equal to 2. Therefore, four squared equals x plus 1 over x minus 3, or 16 times x minus 3 is equal to x plus 1. So 16x minus 48 is equal to x plus 1, or 15x equals 49. So x equals 49 over 15. All right, any questions on using logarithms to help solve equations?
No.
All right, so all these are just properties of logarithms in algebra again. Okay, so I'm going to kick this up a notch. We'll do some calculus. I guess one more algebra first, then we'll get to calculus. But I've got this exponential growth and decay problem. Right now, our pressure is 781 millimeters of mercury at 2 kilometers below sea level. Pressure at sea level is 764. I want to know what the pressure would be at 3.4 kilometers above sea level. What equation am I using? How do I set this up? Is this growing discretely or continuously?
Continuously.
Continuously? Okay, so we'll use A of t equals PERT.
PER square root RT.
So this is P e raised to the RT. P is your starting amount or your principal. R is your rate. T is how many times that you have compounded. A of t is your amount right now. So for us, I'm compounding at our amount of kilometers above sea level. And I've got a rate of decay in our pressure. Because our pressure decreases exponentially as our elevation increases. Okay, so I was told that A at negative 2, so if we're in a valley 2 kilometers, 0.2 kilometers below sea level, is 781.8, which according to this formula would give me my pressure at sea level, 764, e raised to the rate, which we don't know yet, times how many times we've compounded, which is our input, or negative 0.2. Okay, so I'm going to solve for the rate using this equation. So I could say 781.8 divided by 764 is equal to e to the RT. Take the natural log of both sides. Oops, we actually know what our time is. That's negative 0.2 for how many times we've compounded, and I can divide. Negative 0.2 is negative 1/5, so I can just multiply by negative 5 on this side if I want. So I could say my rate is equal to negative 5 natural log of 781.8 over 764. Okay. Any questions on how I got the rate? I'm not quite done yet. Everyone's super quiet again. We've got all the mics muted. Okay, I'm going to take that as a no. So we've got our rate. I wanted to know what the pressure would be at 3.4 kilometers above sea level. So I'm just going to plug in 3.4 and we'll get our final answer. So at 3.4 kilometers above sea level, we'll have 764 e to the rate times our time, 3.4. I guess we'll simplify a little bit. We'll throw it in the calculator. Okay, so right now, I am multiplying this logarithm by 3.4 and by negative 5. So I can say this is 764 e to the natural log of 781.8 over 764 raised to the negative 5 times 3.4. Okay, so this e and ln e will cancel. So that gives me at 3.4 kilometers above sea level, we would have this much atmospheric pressure. And we can plug that in. So that's 781.8 divided by 764, raised to the power of, I guess I'm just going to leave this. This is negative 5 times 3.4. Gives me 516.48 millimeters of mercury for our atmospheric pressure. Any questions on what we did? Okay. Assuming that our rate is constant, if I wanted to figure out what our rate of change was at 3.4 kilometers, so how fast is the pressure decreasing at 3.4 kilometers, we could derive this equation. So I'm going to get a general form first here. When I derive this general form, I would get dA over dt is equal to my pressure I have at sea level is a constant. My rate here is also a constant, but how far you are above sea level is not a constant. So I could say this is, if I derive this, I would get Rp e to the RT in terms of time. Then you could plug in your rate, amount at sea level, your rate, and then where you are right now, and that would tell you how fast the pressure is changing as you pass that point. So as you pass 3.4 kilometers, how fast is the pressure changing? Okay, units would be millimeters of mercury, so that's pressure, in terms of your times compounded, which in this case is measured in kilometers. So how high you are above the surface, above sea level. Okay, any questions on anything? All right. Again, we've got the test coming up on projectile motion. You've got weight and tension problem. There's logarithms for properties of logarithms and rewriting. And there's the compound interest and exponential